Okay, hello everyone. Welcome to the home studio. We are going to be talking about the muscular system today, and it is a little bit lonely here. I miss seeing all of you. Talking to a camera is less fun, especially with muscles because there's so much demonstration and interaction. So I'll have to add some other videos to this where I can do more hands-on things. For right now, I'm just going to try and get through these slides, talking about it, and do some separate videos of demonstration. So sorry that makes everything a little bit boring, but desperate times that we're in here. So intro to muscular system today. You've already learned a lot of things about the muscles, origins, insertions, actions, innervations. Now we're going to get into a little bit more of the microanatomy, and the characteristics and how they function together and things like that. So we'll kind of go through this today. We won't talk about levers because we covered that when we were talking about bones. So some characteristics of muscles. They are contractile. Obviously that's kind of the main attribute that we think of with a muscle. It can contract. It's extensible, so we know that it can stretch. It is elastic, it can come back to its resting point. It has those electrical properties that makes it excitable, and it's also conductible, meaning that it can transmit an impulse, which is important when we talk about nerves, and particularly in different types of muscle tissue. So 3 types of muscle. I'm sure you know these. Skeletal, which is primarily what we're going to talk about in this class, and then cardiac and smooth. So skeletal muscle, the innervation comes from the somatic nervous system, right? So a lot of our muscle system makes up our body weight. It makes up our ability to move. It is related to posture and keeping us upright, creating body heat, lots of important things. Some of the attributes microscopically, you would see that these fibers are striated. They have nuclei if you were to look at it under a microscope, and they vary in their appearance. Some have more myoglobin, they are redder in nature. Some have less myoglobin, those are more white. There are different types even within skeletal muscle. Basically there's 3 types. You have slow oxidative and fast glycolytic, and those are kind of the 2 bookends of the spectrum. In the middle, you have kind of an in-between one that's fast oxidative glycolytic, which kind of has attributes of both of those. So slow fibers are more about posture and endurance and being able to hold a contraction for a long time. And then your fast glycolytic are more about like being able to throw a ball. They can function anaerobically, but they fatigue really quickly. So pretty much every muscle in your body has a makeup of all of these. Some people in a given muscle might have a higher proportion of one than another, but most of your muscles will each have some of these. And they're a little bit different in their size, in their color, and that sort of thing. So don't worry too much about all the different types and subtypes, just kind of knowing the basics about the skeletal muscle and those kind of 3 divisions of fibers. Okay, so if you were to look at this is what it would look like under a microscope. You can see high myoglobin content on this one, giving it that red characteristic. You can see the striations also. This chart gives you a nice little kind of summary of what we've talked about. So, and you can see how the different subtypes of muscles, of skeletal muscle, there's type 1 and there's type 2 and there's kind of all of these. There's type 2B, there's different kinds. Don't get too bogged down with that. But this gives you a nice summary of what their function is, whether it's more postural or how fast it fatigues or how vascularized they are and things like that. So to kind of jog your memory on those different muscle fiber types. When we move on to the other ones, smooth muscle is mainly for peristalsis, right? Moving food through the digestive tract. This is not the somatic nervous system. This is governed by the autonomic nervous system. Cardiac muscle is as well. And so you don't have these nice linear organized muscle fibers. That striation is absent if you were to look at this under a microscope. They do have nuclei, and they look a little bit like this under a microscope. So you see that there's not those nice striations that we saw earlier, and you see the hollowness of these structures as well. Cardiac muscle, controlled by the ANS also, and really just found in the heart. Okay, that organ has cardiac muscle, and it's very unique. So in this case, you'll see those striations again. You'll also see the nuclei, but they are a little bit different given their function. And we won't go too much into the physiology of how that muscle pump works. You have the AV node and the way that muscle system coordinates to be able to form a pump is pretty unique. We won't talk about it so much in this class because we're primarily concerned with the musculoskeletal stuff. But you can kind of get an idea here of what it looks like, and obviously the function that it has, right side, left side. Okay, when we talk about muscles, you're very familiar with the origin and the insertion, and I think you probably know by now that the origin tends to be the more proximal attachment, and the insertion is more distal, and usually it is the insertion that's being pulled towards the origin when a muscle contracts. Okay, at least concentrically, right? A couple of other terms you already know. Tendon is that interface between muscle as it approaches its attachment to the bone, that white glistening connective tissue. Fascia we've talked about, aponeurosis we've talked about as well. So muscle fibers, or a muscle, is composed of lots of different fibers. So these individual muscle cells are bundled together and bound together. They have fascia surrounding them. You've cut like a piece of steak and seen those different striations and the marbling of that if you cut a cross section. If you were to tear a piece of meat, it would tear along those fascial lines between the bundles if you were to rip it like that. If you cut it, you can see that nice cross section, and you can see all of those, that fascia surrounding each of those little fascicles. So when we talk about the fascia that surrounds those, endo, you know that prefix, meaning kind of innermost, usually epi is outermost, and then the peri is in between those. So if you can kind of see that here, if you have just this little muscle fiber here is wrapped by the endomysium, and then as you get another bundle together, you have perimysium around that, and then if you have a whole muscle, you have the epimysium around the whole entire muscle there. Okay, this kind of fascial stuff is pretty dense connective tissue around the very outside. You get to have some neurovascular kind of structures in there once you get into the more interior part of that. Okay, and you can see that. This is how meat, if you cut it, you can see that grain there from these little individual bundles. Okay, another little view of that there. Okay, and you can see that again, the fascia that surrounds each of those, and this is breaking it down even farther. If you take that muscle fiber, now you've got all of these myofibrils inside of that, and if you look at that close up, you're going to see these different bands, and you've learned about those in physiology, your Z discs and all of those different parts of the muscle. We'll talk a little bit about that, but not too much. But just to kind of jog your memory, you can see from Z disc to Z disc, you have that nice sarcomere. And that is what we talk about when we talk about the contractile unit of a muscle. It's that sarcomere is from the Z disc to the Z disc. And you can see, if you look closely, that actin and myosin in there that overlap to contract or shorten the muscle. Okay, another little view of that there. You can see that yellow is the endoplasmic reticulum. Okay, you've got mitochondria, just kind of all the typical cell parts. As we go down into this a little bit more deeply, again, just kind of knowing the basic parts of the muscle cell. Okay, you've got the sarcolemma, which is that plasma membrane around the outside. That membrane will dive deeper towards the more internal part of that. It has these kind of deviations that go in. Once you're in here, this is called your T system. You have these transverse tubules here, and you also will have the cisterns where those kind of expand, and you have those in large portions of the sarcoplasmic reticulum, which you can see in here. That's more of this green part that's more longitudinal. These transverse ones are transverse. And of course you've got calcium and your other ions circulating in there, which is all part of how the muscle knows to contract. Okay, so kind of just remembering and keeping straight some of those terms. It's easy to get sarcoplasmic reticulum and sarcolemma mixed up. Just kind of remember a little bit about what's what. Okay. So again, the sarcomere is the functional unit. Within that sarcomere, you have your actin and your myosin filaments, right? And they overlap. You've got the myosin are thicker, more that golf club shaped kind of arrangement, those two heads, and then the actin, the very thin filaments. And you know that those slide across each other, attach and pull closer, detach, attach again and pull closer, and that's how the muscle shortens. That's how it develops that tension, is that continuous cycle of those myofilaments attaching and sliding and attaching and sliding. Okay, so you can see those there. So when a muscle contracts, again, this is your sarcomere, Z disc to Z disc. Here is your myosin and actin, and as the muscle contracts, these will approximate, these two Z discs come closer together as the actin and myosin pull them closer together, and you develop tension in the muscle that way. Okay, so a little summary here on how a muscle contraction works. Again, don't get bogged down in the physiology of it. If you just kind of remember the basics of the process, you have that nerve impulse coming, okay, that motor unit, that nerve comes in, acetylcholine release, that neurotransmitter, and that binds on the motor plate, and it releases the calcium. The calcium binds to the troponin, and that moves the tropomyosin out of the way, and then you can form your cross bridges. As long as the calcium's there, it will continue forming those cross bridges to keep shortening. Calcium gets pumped out and the muscle contraction stops. Okay, that's kind of the nutshell version, which is sufficient for us. Just another view there of all of those parts. Okay, we're going to shift now. That was sort of the microscopic, the review of the physiology, and now we're going to get to some of the more functional parts of muscles. So when we talked about muscles as an individual muscle, like the pec major or the biceps or the quadriceps, whatever, we'll talk a little bit about them more globally now. So you have muscles that are named by various ways, right? And you know all the names of most of the muscles of the upper and lower extremity. And so you know that they're often named by their shape, or like the deltoid, triangular, comes in on the deltoid tuberosity to a very fine triangular point there. By their size, the gluteus maximus, they're named by some characteristic of it, how many heads it has, or how the fibers are oriented, are they transverse, or other things. It's helpful when they're named by what they do or where they are, right? Those are kind of the best ways if you're trying to learn what they do and what their purpose is. So sternocleidomastoid, very helpful to remember where it originates and inserts if it's all in the title, right? Okay, and then by body region obviously helps as well. Okay, so when we name fibers or organize them, sometimes that's by the arrangement of those fibers. So you can have circular muscles, which you can imagine are more for like closing openings. Okay, you have an orbicularis oris, you have an orbicularis oculi that help close those openings, right? Those are circular muscles. They just go around and help close. You have pennate muscles, which some are bipennate, some are multipennate, unipennate, whatever. This kind of, if you think of a feather, you've got a nice tendon coming down and fibers kind of obliquely inserting into that tendon. It could be on either side of that, could just be on one side. These are particularly suited for force. They are not so good at allowing a lot of range of motion, but they are better for force. Some of the more triangular shaped muscles, like the deltoid we mentioned, makes for a more versatile function. So for example, with the deltoid, we know that it's a shoulder abductor, but your anterior deltoid also can horizontally adduct and it can internally rotate, and your posterior part of the deltoid can do the opposite. Okay, so you have options there with that arrangement of fibers. Parallel muscle, kind of we think of the biceps as an example of that. Very longitudinal and parallel muscle fibers. Fusiform is an example of this. It's got kind of a tendon at each end attaching to the bone. These muscles are geared towards speed and endurance and range of motion, and less about power and force. Okay, and that's what our arms more so are used for functional activities, feeding ourselves, reaching, putting things away, opening a door, or things like that. And they're not brute force kinds of things, but we need more range of motion for that, and so that accommodates that better. Okay, you can see pictures of these examples of different kinds. Again, different texts will sort of have maybe a few different classifications in their umbrella here as far as the terms, but you get a basic idea here. Okay, so think of examples that we've learned and how you would classify them. Okay, how does a muscle generate movement? We've talked a little bit about the microanatomy, the actin and the myosin, how those overlap and bind together and create tension in the muscle. And we've also talked about how important it is where the muscle crosses the axis or crosses the joint relative to the axis of motion, and that having a bearing on what that muscle does. So muscles that cross anteriorly tend to flex the joint. Posteriorly tend to extend the joint. Sometimes as you move that distal segment, sometimes a muscle that started more posteriorly, maybe now its insertion has come anteriorly and now it has a little bit of a different function. Okay, so thinking about all of those things we've already mentioned, and then a few more things: how big the muscle is, the angle of pull that it has, or the mechanical advantage that it has influences how much tension it can develop. And then also the recruitment of motor units. Okay, so what does that mean, right? If I'm going to go to pick up something that's really lightweight, okay, this is lightweight, and my body already knows and can anticipate how many motor units to recruit, and I can go and pick it up and I have just the right, I'm not like shooting it up in the air, or I'm not like, whoa, that's so heavy. I can anticipate that and I can recruit the right number of motor units. Same thing if I was going to go to pick up something heavy, right? Your body will do the easiest thing first. If I don't need to recruit a lot of motor units to pick that up, then it won't. It'll just fire to maybe one motor neuron to pick that up. If it's a heavier thing, then it fires to more motor units. Okay, so we talked before about different fiber types. A motor nerve only will innervate fibers of all the same type. So one nerve firing will not recruit both slow oxidative and fast glycolytic at the same time. It only can activate the fibers that it innervates, and they are always of the same subtype. So in places where you need really fine and controlled motion, you'll have a nerve that only innervates maybe 1 or 2 or 3 muscle fibers. For example, the eye, right? I'm able to control my eye movement really well. If I want to look, right at that window or right at that light switch, I can turn right to it and dial it in really easily because I have so many nerves that can control that. Okay, one nerve only goes to a few muscles. In like your postural muscles, let's say my erector spinae, I maybe have one motor nerve and it goes to a whole bunch of muscle fibers. Okay, because I don't need fine control. I just keep me upright, do your slow oxidative thing, and that's all we need. Okay, so thinking about the innervation of it, some other things that can affect how well the muscle will generate tension is the length of the muscle, so a length-tension relationship, which we'll talk about in a minute, and the velocity as well, how fast it's shortening. Okay, so a couple of new things to think about today. When we were talking about muscles of the lower extremity, we have talked about whether or not that joint crosses, or that muscle crosses one joint or multiple joints, and started to think about how that impacts what it can do functionally. Okay, so multi-articular, mostly these are 2 joints, sometimes 3 joint if you think about some of your wrist and finger flexors and extensors. Some of them cross the elbow joint as well, right? So you have 3 there. Often it's just 2 joints. And there's some unique characteristics that we're going to talk about with that. It's nice to have 2 joint muscles because then we have less muscle bulk in the body. Okay, we can kind of be more efficient and trim that down. Your innervation is then less complicated because you have less muscles. So it's helpful that way. And you can coordinate your movements pretty well also. Now, there are some disadvantages, and there are 2 terms that are really important to know: active insufficiency and passive insufficiency. So active insufficiency, there's a couple kind of terms here that can clue you into what's happening. So when it says here to cause, or when it says here to allow, those can kind of clue you into this is an active thing, a contracting thing, and this is more a passive thing that's happening to the muscle. So basically, active insufficiency means that you cannot generate maximum force in that muscle actively, meaning me trying to do that, if the muscle is shortened over both of the joints. Okay, so if I have let's say I'm talking about a muscle that's on the anterior side, so maybe I'm talking about my rectus femoris, crosses the hip, so it has a little bit of hip flexion capability, mainly it's a knee extensor. So if I have shortened that muscle actively, so if I have come into hip flexion and then I want to shorten it over the knee as well, so now I'm in knee extension, right? I've shortened it over the hip joint and now I've shortened it over the knee joint. In this position, my quads is not very strong, right? That's an awkward position even to like kind of put yourself in to think of doing anything functionally like kicking a ball or whatever. Okay, so if you've shortened it over both of the joints, you have now kind of taken your actin and myosin all the way across. They're too far apart now, they're too overlapped to be able to form good cross bridges and generate tension in the muscle. Okay, passive insufficiency. This means that a muscle does not have enough length at rest to be able to lengthen over both of the joints it crosses at the same time. Okay, so think about if you're laying on your back and you have your leg out straight, so your knees straight, you're laying on your back. If you come into hip flexion, okay, but I'm keeping my knees straight, it's eventually gonna get tight back there, right? You're gonna feel that in your hamstrings. In that position, I have lengthened it over my hip. That muscle's been stretched over the hip, and it's also stretched over the knee, okay? If you were to slack it off either of those joints, you'd be able to get more range of motion in either one, right? So if I'm laying on my back, I'm gonna lift that leg and I'm gonna get, a little bit off the table and then it's gonna hurt. But if I bend my knee, now I can bring my hip into more flexion, okay? Because I've slacked it off at the knee. I've bent that knee, so now it's not being stretched at the knee. It is still being stretched at the hip, but now I can bring my hip into more flexion because I've stopped making it stretch at the knee also. Okay, so you don't have enough length in the muscle to stretch over both of the joints at the same time. Okay? We've talked about muscle contractions before, we've talked about levers before, but basically, what are your muscles trying to do? They're either trying to move something, or they're trying to keep something from moving, or they're trying to stabilize something to help another muscle do something else, right? Those are kind of the three roles in this muscle contraction. This is a review, isometric contractions, staying at the same length. Isotonic can either be shortening or it can be lengthening as that tension is developed in the muscle. And isokinetic, is where the speed stays constant and kind of need a machine to do it. It's not really something that happens naturally. So that concentric as you're going there, and then also if you're coming this way, it's an eccentric contraction of the triceps, controlling that arm coming down. Okay, so those are not new to you, and it is really pretty amazing what people can do as far as changing their muscles, strength, and otherwise. Functional muscle groups. So often we'll talk about muscles in a functional group. Like we've kind of learned all the muscles individually, but a lot of the times when we want to consider them, we're considering them in a functional group. Okay, we'll talk about, for example, hip extension. What are your hip extensors? You've got glute max, you have hamstrings, and maybe you have some other smaller muscles that can do that as sort of a secondary action. Okay, so we talk about them in these functional groups: the hip flexors, the knee extensors, etc. And for the most part, this is how muscles work. They work together, they work in groups, and even muscles on both sides of the joint or both sides of the bone will work together. Your quads and your hamstrings often are contracting at the same time. We call that co-contraction. Okay, the agonist is the main muscle that's causing the movement. Okay, so when we talk about elbow flexion, what is the agonist for elbow flexion? It's the biceps. That's the main muscle that's performing that action. The antagonist is the muscle that has the opposite action as the agonist. So if we continue this case, our biceps is the agonist, the triceps would be the antagonist. Okay? You also have muscles that are stabilizers. So these are muscles that are basically stabilizing in order for another muscle to be able to do its job. So you can have stabilizers that are functioning statically or dynamically. So statically, let's say I'm doing some leg raises, I'm contracting my abs, but nothing's really moving there. My leg is moving, but my abs are really pretty static. If I'm doing something with my shoulder, maybe I'm moving my upper extremity in different ways, and my scapula therefore is also moving. Remember scapulohumeral rhythm, right? Like there's some shifting there and rotation with the scapula as I go through those motions. So different muscles that attach to the scapula are getting recruited to keep that scapula stable so that the other muscles that are trying to move my arm can accomplish that. Okay, so stabilizer. Okay, a synergist. A synergist, this one's sometimes a little bit trickier. So a synergist is a muscle that has at least one antagonistic action to the agonist, and it contracts in order to help the agonist be more efficient. It usually eliminates some other movement to be able to make the other one function a little bit better. An example of this is in your wrist and finger flexors and your wrist extensors, that relationship there. So if I'm trying to grip something, I want to hold something really tightly, my finger flexors are going to be the ones to do that, right? I need to grip it tightly. So my finger flexors will flex and grab onto something. Well, you know that the finger flexors also cross other joints than just the fingers, right? So they also cross the wrist. And when they contract, they can't really selectively say, well, I don't want to flex the wrist, I just want to flex the fingers. It just contracts, right? And it brings the two ends together. So if my wrist flexors are the only ones working, I'm going to end up in a position kind of like this. They can't do one or the other or control that separately in any way. It's just that's what it is. But once I get my wrist into too much flexion, my fingers are less able to close. And think about why that is. We'll come back to it. So I need my wrist extensors to contract which keeps my wrist in extension so that my finger flexors can grab onto that tightly. Okay, so the wrist extensors are a synergist in this case. They have an antagonistic action to the flexors. Okay, they're extensors. They contract, which keeps my wrist in a good position that gives my finger flexors a better ability to contract tightly and hold on to something. Now, why do I have a weaker grip when I come into more wrist flexion? We talked about it earlier. It is an issue of active insufficiency. As I shorten along this joint, I can't also shorten along this joint, right? Your actin-myosin overlap too far, your leg tension is thrown off. I can't generate good force and try it. Flex your wrist and see how easy it is to hold something tightly or to make a tight fist when you're all the way flexed. If you even just sit here and let your wrist fall naturally into flexion, what happens to my fingers as I do that? They extend, right? They naturally extend. If I were to go into wrist extension, they end up curling more, right? So I go from here, they extend, I go back into extension, and they end up flexing more. That has to do with insufficiency, okay? In the one case where I don't get a strong grip here, that's active insufficiency. I've shortened that muscle too much that it can't generate a lot of tension. Okay, I can't squeeze that tightly actively. Now, if I come back here, why do my fingers curl? If I'm just coming into, and you could, with your other hand, accentuate that a little bit, but this passive stretch now I've stretched here. If I've stretched a lot here, I'm not going to be able to stretch a lot at my fingers as well. Okay, so that gets really uncomfortable if I try and do that. That's passive insufficiency, because I can't stretch fully here and expect to stretch fully here. It doesn't have the length to do that. Okay? Fixators are another kind of stabilizer. Your rotator cuff is really good for this. It's stabilizing the scapula so that your other upper extremity muscles can have a stable platform to pull from. Okay, this is especially important in two joint muscles if you want the proximal joint to not move so that you can move the distal one. Okay, then you're relying on some fixator stabilizer muscles. Okay, a neutralizer is a muscle that has a common and an antagonistic action with the agonist. Sometimes an example of this is even within the same muscle, like the deltoid that we talked about. The anterior deltoid and the posterior deltoid have opposite actions, but they can all work together and contribute to abduction of the arm in the pure plane, right? Because they've canceled out those other motions. When we talk about the hamstrings and the biceps femoris inserts laterally, the semitendinosus and the semimembranosus come in medially. Those tend to, in addition to extending at the hip, flexing at the knee. At the knee, they also have a little rotation there because they come in laterally, right? So if you're contracting all your hamstrings together, that external rotation of the biceps femoris and that internal rotation of the knee on the medial side cancels out, and you can just have pure knee flexion there. Okay, that's called neutralizing. Okay, co-contraction, kind of mentioned. This is very common, happening all the time. It gives the joint more stabilization and also muscle control. It approximates the joint to keep it nice and together. It's helpful for postural control and balance corrections. And you can see that if you were to stand on one foot, you're kind of contracting. Both sides of that joint are sort of on the ready, right? So that if I were to lose my balance a little bit, and even if I look like I'm standing pretty still, if you look at my foot, you'll see those tiny little aberrations. those muscles are kind of on guard on all the sides of the joint to be able to correct that. If I'm, losing my balance one way and, I gotta evert to stay on, or I need to plantar flex to come back, those subtle things can happen very easily if you've got the contraction already happening on either side of the joint. Okay, the length tension relationship. So we've talked about how with active insufficiency, the muscle is too short that it can't generate a lot of tension, right? So there is this optimal window of muscle length to be able to develop the most tension. The optimal length is about 1.2 times the muscle's resting length. If you are shortened too much, you've overlapped your, can't form your cross bridges because they've just slid past each other. And then the same thing, if you're lengthened too much, they're too far apart to be able to form those cross bridges either. So there's kind of this perfect little window. And they found that with that ideal length at 1.2, if you put the muscle on a little bit of stretch before some sort of event, an activity, or a sporting event or something, if you put that on a little bit of stretch, that you can get more power when it contracts. And so you'll see this in sports. If you look at the posture look at track athletes, why do they start in those starting blocks? They put that gastroc in a little bit of stretch so that they can have a strong push off when that gun goes off. Okay, so putting it on a little bit of stretch. I use this concept all the time with my, often they're elderly and they're certainly not any kind of elite athlete. If I give a little bit of, maybe someone's coming out of a total knee replacement or surgery of some sort or an injury, whatever, as you're trying to rehab and get that strength back and get that neural input coming back to that muscle, before I have them do an exercise, sometimes I'll give a little bit of stretch. If they're doing like a long arc quad type activity and I do a little bit of stretch and help that quad fire, then put it a little stretch and then it will kick up a little bit easier. Okay, so these have to do with the contractile and the non-contractile elements. If you kind of can remember the series elastic component and that sort of thing, they're in series and sort of like a spring can hold that to make a nice explosive movement when they're needed. So that's the idea, and you can see that here. Here's your length tension relationship. If you're too short, not a lot of tension. If you're too long, not a lot of tension. So there's kind of this nice little window right in there. Okay, and then we mentioned also the force-velocity relationship. This one is a little bit more complicated, and so don't worry too much. You can see from this that an eccentric contraction, you can develop more tension and more force in the muscle than a concentric contraction. But mostly what I want to point out is as your shortening velocity gets faster, so the quicker you're shortening, the less tension you can develop. So if you think about, if I have like a 2-pound little dumbbell in my hand, I can go super fast, right? And it's super easy and no problem. If I slow it down, I actually am able to generate more force in the muscle, and it actually will seem harder. Okay, you can try and experiment. Grab a can of soup or something, do it really fast, and then do it really slow, and you'll feel that more tension is generated. You'll feel that it's harder to do that. So just some relationships to think about, how that affects the muscle. And here you can see that track athlete in the starting blocks, you're putting this gastroc and you're plantar flexors and a little bit of stretch so that they can explode off of there. Same thing, you know, a swimmer. So it gives a more forceful contraction if you can put it on a little bit of stretch first. Okay, that's your muscle unit. This is the last set of slides that you'll need for your lower extremity exam coming up. So, thanks.